Hello everybody. Together with PLDA, Avery Design System and ALDEC, we are going to present you and demonstrate our newest PCIe 5.0 IP with verification IP from Avery, UVM simulation, and debugging environment in Riviera-PRO. Our presenter are Luis Rodriguez from Avery, Tampat Banca from PLDA, and me, Mike Patsua from ALDEC. Tampat, your turn.
Yeah, this is Sampath Banka. I'm from PLDA, working as Senior Application Engineer, right from San Jose office. And I'm here to discuss about PLDA, which is a 20-year plus company developing variety of high-speed interconnect IPs. And the company's portfolio includes PCI Express, as well as CXL, C6, and Gen Z. And as a company, we involved in understanding your architecture requirements right from reviewing your choices, propose your design optimizations, and provide the best-in-class details suitable for your application. And PLDA supports your design cycle right from architecture phase, RTL, and sign-off, and also assist you while the post-silicon validation in the lab. And it covers a majority of steps involving your clock and reset strategy, right from power-up sequence and IP configuration parameters, and how to use built-in DMA engines, etc. And also we'll help you in the verification environment and PHY integration as well. And this IP or all our PLDA IPs will be robustly verified in-house using multiple industry standard VIPs, including Avery. And also PLDA has its own in-house verification environment. And Express Rich Core is integrated with 40 plus PHY variations from almost all the standard PHY vendors in the industry. And also we develop a prototyping platform which is used for validation also. And that is the standard Gen 4 host in PCIe workshop. Next slide, please. And coming to the features of the PLDA Express Rich Controller IP. So this IP is supporting all the modes, right from root port, endpoint, dual mode, and switch port with native interface. And this IP is designed to PCIe 5.0 specification, supporting up to 32 GTS, and configurable as by 1 to by 16 lanes. And it is multifunction and SRIV capable up to 64 PFs and 512 VFs. And VFs can be dynamically allocated to each PF. And it has a built-in RAS feature for reliability, availability, and serviceability. So this module adds more vigor to in-depth failure analysis by injecting the errors on the both TX and RX path to check your application as well as the DUT behavior. And Express IP is one that we take to the PCIe workshops, and it is PCIe certified for Gen 4 speed in August 2019. And we support many of the ECNs apart from the PCIe base spec, which will be very useful for different kinds of applications like TPH, TLP processing hints, which optimizes the memory bandwidth, and multicast, PASID, process address space ID, and ACS, access control services, which basically controls which device needs to be allowed to communicate as part of ATS. And precision time measurement, PTM, DPC, atomics, etc. So these are the ECNs that are implemented in the IP on top of the PCIe based specification. And it is silicon proven with multiple tape outs and been using in multiple FPGA based platforms. So that's the introduction of the PLDA IP portfolio. And now Luis will take over to discuss more on the Avery part of this presentation.
Hi everyone, this is Luis Rodriguez with Avery Design Systems. I've been with Avery about 15 years working on developing verification IPs and enabling customers during evaluations and project ramp-ups. And so Avery is a third-party vendor for verification IP. We have one of the most complete VIP portfolios. So that includes PCI Express, USB, NVMe, AMBA, DDR, different DDR protocols. One thing that differentiates Avery is that the VFMs are all built in system Verilog, and so they're very robust and flexible, runtime configurable. There's protocol checkers built in, which we are clear about and provide our customers with a spreadsheet of all the protocol checks included in each one of the VIPs. We have full compliance test suites. The native UVM feature allows you to integrate it into a UVM environment seamlessly. So you drop the VIP into the UVM environment directly. There's no wrapper code. And we provide you very straightforward functional coverage as well as checklist coverage. And even though we're a smaller vendor, we're a private company, we're actually the leader in the SSD space. So PCI Express and NVMe, probably more than half of the companies developing SSDs with NVMe support use Avery. And we're also leading the charge with CXL and CCIX as well, so next generation of PCI Express. And one thing we do differently is we partner with verification IP companies like PLDA, and we do that to ensure the quality of the verification IPs. And so for PCI Express specifically, we talked about, all the VIPs are native system Verilog. This PCIe VIP is the only, it's the only verification IP out there from the main vendors that supports native system Verilog in a PCI Express VIP. So it simulates faster when compared to other VIPs that use other languages internally and then have system Verilog or UVM wrappers. It's easy to integrate the VIP because it's class-based. You can create arrays of VFMs, for example, if you support things like bifurcation, or if you're testing a retimer or PHY. We provide you transaction classes to enable the user to generate stress type of test cases, large amounts of data movement, writes or reads. And under the hood, the BFM is always randomizing itself. The transaction, data length, PHY layer, the config space, it's all randomized. So the BFM looks like a completely different link partner every time you run with a different seed. And we also provide you over 35 callback points. This diagram only shows a subset, and those can be used for scoreboarding, but also for error injection. And so you can catch packets at different callback points and inject errors, for example, invert fields within the BFM, the TLP, or corrupt LCRC. You can also catch the packets or DLPs at lower levels and inject low-level PHY errors. And so it's a very flexible methodology for injecting errors. We also provide per-layer trace files, which we will look at during the demo in more detail. And overall, the VIP is simpler to learn. If you have a basic understanding of PCI Express, the tracker files will be easy to understand, and enabling test cases will be straightforward. We try to provide less APIs and more callbacks for error injection. So the basic functionality is simplified for users, and if you need to create error injection scenarios, then you typically rely on the callback points. We also provide a full compliance test suite. This is a superset of the PCI-SIG compliance. It's over 700 test cases that includes the PCI-SIG compliance. Plus, 80% of this test suite is Avery specific, targeting compliance to the spec or coverage.
The whole design will be simulated and analyzed together with ALDEC Riviera-PRO, which includes integrated debug environment, data flow visualization, post-simulation debug, coverage viewers, metric-driven verification, design rule checking, and fast waveform viewer, which correspond together with the message window. Also, we provide the UVM graph, UVM hierarchy configuration, and will be also shown finished state machine in graphical way.
now we move on to the main part of the demo. And so first off, we will review the design configuration. So that's the PLDA IP and the Avery BFM configuration in the test bench and the UVM environment, as well as the main sequence that we use for this demo to showcase PCIe Gen 5 and air injection, as well as debugging capabilities within the Riviera-PRO tool. All right, and so this is the high-level diagram of the UVM environment along with the test bench. And so in the test bench, we have the PLDA IP. And Sampath, you can introduce that portion for us?
Yeah, sure. Thanks, Louis. This is the PLDA IP used in this environment, and it is configured as an upstream port. And all the layers are basically be tested in this part of the demo. So this IP has a pipe interface on the other side and the user application on the other side. User application interface on the other side. The pipe interface is basically connected to a pipe box that is basically connecting the test bench interface. And on the other side, there is a custom PLDA application layer that is basically doing the transactions as an application. And coming to the transaction layer interface, it is a TL transmit and receive data path, as well as the debug ports and error reporting ports are available on the PLDA IP. And it is configured as a Gen 5 endpoint by 16 lane. And Louis, that is part of the PLDA IP, and you can take over to explain the remaining part of the test bench.
All right. And so in the test bench, this is essentially a Verilog module. The PLDA pipe interface is then connected to a pipe box from Avery. This is just a pipe-to-pipe connector. And so this supports different modes of the pipe spec. You know, there's pipe 4.2 and 5.1. It also supports the low pin count and SerDes architecture. And so PLDA connects on one side to this pipe box. This is the upstream port. And then on the Avery side, we have a root complex BFM. The BFM is a native UVM agent. And so the BFM lives inside the UVM environment. It connects through a pipe interface, which is passed through UVM config.db from the test bench to the UVM environment. And so that completes the integration of the PLDA IP with its own custom app connected through a pipe interface to this pipe-to-pipe connector. And the pipe connector connects on the other side to the Avery BFM, which is living in the UVM environment. And so we also have UVM test cases which drive the traffic through the BFM. And so if we switch over to the Riviera-PRO tool, once you compile and start simulating the design, this will generate a UVM graph as well as a UVM hierarchy of the UVM environment. And so if we start from the UVM graph, you will see the test stop, which instances the environment, which has the root complex BFM instance. So this is the UVM only view. And so that would be this portion of the setup. And so there's also an endpoint here, which is made passive in this simulation because the root complex is talking to the PLDA IP. If I open up, this is the Avery root complex class, so you can directly open up the different classes. If we go through the UVM environment, it's a straightforward UVM environment. It extends the UVM environment class. We simulated this. You can see the BFM instance directly in the UVM environment. There's a build phase, connect phase. In the build phase, we create the BFM. And this was simulated, so you can see in green this is showing coverage, and the parts that are in red, it's showing branch coverage is not 100%. So in this case, we are always creating the root complex BFM. And so that's why this line here shows up in red. And so this line here, we create the root complex BFM. In the connect phase, we go ahead and do a UVM config DB get to get the root complex virtual interface. So if we go to the diagram, that line is just getting a pointer of the root complex virtual interface from the test bench into the environment. And so any signal changes that the BFM does are reflected in the test bench, of course. It's essentially just passing a pointer through UVM config DB. And in the run phase, we just essentially decide what type of device this is. So the BFM can be configured as a root complex in this case, and then we start the BFM. So that's the UVM environment. You can also see in the hierarchy view, you have the environment, the endpoint, the root complex. If I open up the root complex, you will see the different analysis ports. Those can also be seen here in the UVM graph. You can see the different analysis ports, which match the callback points. And so we'll be using one of these callback points to do error injection. And similarly, there's a interface here. And so here we can also switch from the UVM graph to the UVM configuration, and you can see the virtual interfaces. So if we go back to the diagram, there's a virtual interface on the root complex BFM side, a virtual interface on the PLDA endpoint IP side. So if we click on one of these, you can see that this interface is fully configurable for different data widths and clock rates following the pipe spec. And there's different modes that you can also configure, things like configuring the P clock as a phi input, which is supported by the pipe spec, or generating a reference clock for a design. You can configure as a low pin count mode, and you have several other controls, and you can also, of course, see all of the different pipe interface signals in here and show these on directly jump to the waveform. On the test case side, the test case will initiate a sequence. The sequence is usually making API calls. In this case, it's going to be generating transactions which generate TLPs, and we use a callback point as well. So you can see the Avery BFM, of course, mirrors the PLDA IP. It has a transaction, data link, and a phi layer. And so there's a transmit and receive path. And there's multiple callback points. We'll be using one of these callback points to catch TLPs and inject errors. And so if we go back to the Riviera tool, and let's open the sequence that we are running. The sequence itself is extending this UVM sequence base, which extends a UVM sequence item. And the main parts of the sequence are within the body. We get a pointer to the BFM from PSequencer. This waits for the full BIOS enumeration to complete. And so in this setup, once you reset the PLDA IP and the Avery root complex BFM, the link will automatically link up and will go through BIOS enumeration. And so this line waits for BIOS enumeration, and then it will repeat creating transactions. And so this transaction is just defining a chunk of memory to either read or write. And so we give it some constraints. We constrain the length. This is going to be a write first. And so it will be generating write transactions from the root complex BFM, the BFM will convert these to actual TLPs. And so on the test case, you can just define how many D words to read. It doesn't have to abide by the PCIe max payload size. And in this transaction, we push back random data. And then in a separate part of the code, we are doing a fork. So in parallel to these transactions, we are using this callback point here, TX packet exit DLL. So when the BFM is generating multiple TLPs, multiple write TLPs, this callback point will catch TLPs. And in this case, we're defining a probability of catching those TLPs. And so we calculate a random probability here from 1 to 100. If this number is higher than 85, meaning 15% of the time when we catch the TLP, this callback point will output this TLP pointer. We make sure that it's a TLP. It could also be a data link layer packet. And then if 15% of the time, we will directly access that TLP, LCRC, and flip it. And so that's doing error injection. We're flipping the LCRC. The PLDA IP should report some errors, NAC the TLP, and the Avery BFM will replay the good TLP following the PCI Express spec rules. And then later on, while that's going on, so that error is a recoverable error. So you can randomly inject that error. The PCI Express spec should recover gracefully from that, replay the TLP, and it should complete properly. And so at the end of the sequence, we read back the same memory addresses, and we do a D-word by D-word comparison of the payload. So we will write to hundreds of D-words and then compare that payload. Under the hood, we're doing that LCRC error injection. And so that's the overview of the test bench, the sequence, the PLDA IP integration to the Avery VIP. And now we will move to the main part of the simulation where we will see this sequence in action and the different debug features in both the Riviera-PRO tool, as well as the PLDA debug ports and the Avery BFM tracker files.
Hello, from the summary of this today's demonstration, combining the PLDA, Avery, and ALDEC. So PLDA PCIe 5.0 rich core is basically a highly configurable core where the internal data path scaling is possible, and configurable pipelining and RX stream mode for custom credit management, and L1 PM substrates is supported, and dynamically adjustable clock frequency and many more other features and latest TCNs and clock and power gating are supported in this IP.
And from Avery, we showcased the PCIe VIP, which is a best-in-class verification IP for PCIe Gen 5. It's a native VIP. We saw the direct UVM instance, native randomization, different protocol tracker files for each layer, and over 35 callback points for error injection, which we saw in the LCRC error injection.
Yeah, in Riviera-PRO, you saw that you can run the simulation and debug application core architecture. You can inspect simulation waveform very well. Of course, use the UVM Graph toolbox to view graphical representation of the UVM components, objects, and the transaction level modeling, connection between them, giving user an overall perspective on the test bench architecture and the data flow. You can also use code coverage, functional coverage, and others to analyze the efficiency of the UVM tests for exercising various parts of the RTL code. Thank you for joining the demo. Maybe again. Thank you for joining the demo. Now we are going to provide some company facts.
So thanks again for joining from Avery as well. And you can find our website listed here. You can click on it to view information about the PCI Express VIP and download data sheets for any of the other VIPs we support.
Thanks from PLDA for joining, and please feel free to contact sales@plda.com, and you can also visit our website www.plda.com for more technical information and brochures.
You are greatly welcome also for ALDEC on the ALDEC website. To get much more information, please contact with the support, with the sales, and of course trainings or blogs to get all information about provided solutions like Riviera-PRO, APCIe-Xactor, APCIe-Pro, and others. Thank you again for joining us.